Okay, hi guys. So from the previous lecture, we'll be continuing our discussion. So wherein we saw that A plus the equilibrium graph of the forward direction and backward direction, both uh, after a certain point of time, which is the equilibrium time, goes to a constant state. So we'll be continuing from that. Suppose we have an equation like AG plus BG forming CG. Initial concentration was, let's say, A here and A here, and it was 0. And at equilibrium we have A minus x present of B minus, or rather A minus x only for present for B, and x concentration of present at C. So let's draw some concentration graphs, some snapshots of the graphs. What will happen is, another time is, then we have this graph. So this is concentration with time graph, okay. So here, let's say at time t1, what happens is, this is the rate of forward direction, this is the rate of backward reaction. So concentration of A and B and concentration of C at some point of time, which is t1. Now let's say this this reaches a equilibrium point wherein the rate of forward direction and rate of backward direction is equal at time t2. Okay, and after the equilibrium is reached, we have a time t3 in which the concentration of neither A, B or neither C is changing. Okay, so till point t1 concentration of C is increasing and A and B are decreasing. At point t2, concentration of both A, B and C are getting at some equilibrium point or at equilibrium stage, and then at t3 it's not changing, okay, or it's stable, in other words. So this is the snapshot of how the reagents and products reach a equilibrium state and how they are reaching it. So let's say we have a solid example in which we are taking HI, and this HI is disintegrating into H2 and I2, and at the same time H2 and I2 are again forming HI at the same time. So let's say initial concentration was A and 0 0, and final at equilibrium concentration was A minus x, so it would be x by 2 and x by 2 moles. Okay, so here what we will see is that the concentration of rather this is the graph in which it will not change, but concentration of the two are not yet at a certain point, because concentration of A and B would be rather A minus x. Some minor mistake was done here. Now this is actually x and this is actually A minus x. So concentration of C, so this is not the equilibrium point of time, this is the point of time when both the concentration reach a common point, which is not equilibrium point. I might have told this is the equilibrium point, but this was a silly mistake which I did. So this is not the equilibrium point, rather the concentration or the time at which the concentration of C becomes x and the concentration of A and B becomes A minus x. At that point of time the reaction is in equilibrium, not at this point. This point is simply showing that both the concentration of A, B and C are equal, which is not at equilibrium. At equilibrium the concentration of A is A minus x, B is A minus x, and C is x, just like in this graph. So this is the equilibrium state. So pardon me for that mistake. Yeah, so what would be the graph for this case at equilibrium? So this is the concentration at equilibrium. So what will happen? The concentration with time graph. So what will happen here is concentration of Hi will go down from A to A minus X. This is the concentration of Hi, and concentration of H2 and I2 would go from 0 to X by 2. So this is X by 2 and this is A minus X. Okay, so this is Hi and this is H2 and I2, concentration of H2 and I2. Okay, putting some comma here. Yeah. So let's see another example wherein you have some concentration of N2 reacting with concentration of H2 forming NH3. So let's say initially you have concentration of A as concentration of N2 as A and concentration of H2 as B. And equilibrium, what will happen? Let's suppose X by 2 moles dissociated here, B minus 3X by 2 dissociated from here, or this is the equilibrium concentration of H, and finally X moles of NH3 were formed at equilibrium. So what will the graph at equilibrium look like? Concentration and time. So let's say N2 was coming from A to A minus X by 2, H2 was coming from B to B minus 3X by 2, and NH3 was coming from 0 to X. So this is the equilibrium point, T equilibrium. Okay, so this is the concentration graph of H2. This is for N2 and this is for NH3, where the points are, this was for NH3 it was X, for N2 it was A minus X by 2, and for H2 it was nothing but B minus 3X by 2. Okay, so next let's discuss the equilibrium constants for gaseous reactions. Okay, so we have A moles of A plus B moles of B converting to get C moles of C plus D moles of D. This is the generic equilibrium reaction. So at equilibrium, what we can say that we are talking about equilibrium constants for gaseous reactions. Okay, so we have Kp, which is one of the equilibrium constant for gaseous reactions, which can be written as pressure of C times stoichiometric coefficient of C to raised to the power stoichiometric coefficient of C times pressure of D raised to the power of stoichiometric coefficient of D. Similarly, pressure of A times pressure of B. This is gas constant, equilibrium constant for pressure, and then for concentration we have D divided by A multiplied with B. So PA is nothing but partial pressure of gas A in ATM gas A in ATM, and this is the nothing but the equilibrium constant in terms of pressure. Okay, obviously you can extrapolate it for PA, PB, PB and PC and PD. So I'm just writing for PA So PA means partial pressure of B. Similarly, PB would mean partial pressure of gas B. Similarly for C and D. So this is the gas constant at equilibrium constant at in terms of pressure. This is in terms of concentration. Okay. So in the next lecture we'll be continuing on seeing more on equilibrium constants for gaseous reactions. So till then, good luck and goodbye.